This work is named Synthesis, Physical Characterization, and Electrochemical Evaluation of Catalysts Supported on Carbon obtained from biomass by pyrolysis method and nanoparticles by solvothermal method.
Some technologies like fuel cells, for example, is improve the catalyst, for example, reduce the cost of this. In this sense, it's essential reduce the dependence of precious metals. For example, platinum is the better catalyst, but this face some disadvantage. On the other hand, it's possible use biomass and obtain carbon for different methodologies. For example, pyrolysis. This technology allow obtain high surface area and eco-friendly supports of carbon. In other point, the solvothermal method allow obtain nanoparticles with precise control in size and morphology. The use of these technologies provides an interesting via to produce efficient catalysts for electrochemical applications.
The main objectives of these works are synthesize carbon supports from biomass via pyrolysis, produce nanoparticles by solvothermal method, integrate nanoparticles into biomass derived carbon, perform physical characterization, and evaluate electrochemical performance of these catalysts. General methodology for this work consists in the first stage in the synthesis for carbon from biomass using the pyrolysis method. The second stage is the synthesis of nanoparticles by solvothermal method. And finally, is the support of nanoparticles on carbon to evaluate electrochemical and the physical characterization of this material. The bit analysis shows a strong dependence on pyrolysis temperature. In this sense, the samples with low temperature, M1 and S1, both show a low surface area. This indicate an incomplete development of pore. In the other hand, the samples with higher temperatures, M and S2, show higher values. In this sense, the best was M2. These show a high surface area. The XRT patterns confirm the amorphous carbon nature of both samples, with broad peaks around 2 theta between 22-26 degrees. This corresponding to graphitic planes. The increased pyrolysis temperature indicate the partial structural order. Same image shows an irregular carbonaceous particles with heterogeneous morphologies. EDS analysis confirmed the predominance of oxygen and the presence of different mineral elements. These characteristics of biomass derived carbons, that is the origin of the source of biomass.
FTR spectra show characteristic vibration of oxygen hydrogen bonds, double carbon-oxygen bonds, and single carbon-oxygen bonds groups in M1 and S1 samples. These indicate the presence of oxygenate functionalities. On the other hand, the samples with high temperature shows the intensity of these peaks decrease. These reflect the progressive carbonization and removal of surface growths. This trend correlates with the increase in the surface area and the development of more stable aromatic structures is possible.
On the other hand, the results by nanoparticles bit analysis show a similar surface area. However, the sample that is rich in cobalt allow the development of higher surface area structure. This property is favorable for catalytic applications. The XRT patterns confirm the formation of a spinel in both samples. The characteristic reflections at 2 theta in 31, 37, 44, 59, and 60 were observed. The slight shifts in peak intensity is due to the different molar ratio of nickel cobalt. This indicate maybe a smaller crystalline size and possible lattice distortions could be enhance their redox activity. XRT patterns confirm the formation of a spinel in both samples. The characteristic peaks at 2 theta in 31, 37, 44, 59, and 65 were observed, and this proved the presence of a spinel.
Same image shows the formation of nanostructure aggregates with size in the range of tens nanometers approximately. The morphology was relatively uniform in both samples, and in the molar ratio nickel cobalt 1 to 3 samples uh, show the form on smaller and more interconnected particles. EDS confirmed the elemental composition with nickel, cobalt, and oxygen like the main elements, and slight variations consist in the design of the stoichiometry. The homogeneous distribution of nickel and cobalt suggests the successful synthesis of the spinel phase. With the preliminary results, we conclude that the nanoparticles shows a nanostructured spinels of nickel cobalt. There are successful synthesized and characterized. These show the formation of a spinel phase with nanoscale features. Carbon supports obtained from biomass precursors show porosity and surface functionalities. This provides a promising anchoring site for nanoparticle dispersion. The surface area of spinel were relatively low. The structural and morphologies analysis confirmed their potential as a stable and active oxide catalyst. The nickel cobalt ratio control over physical chemical properties which is expected to impact catalytic performance in energy conversion reactions. And finally, the next stage of this work will focus on optimize the deposition of the nanoparticles onto carbon supports, and this allow the electrochemical evaluations to evaluate their possible application as efficient catalyst for PEMs or water electrolyzers.
Thanks to SECTEI for partial support through project SECTEI 137 2024.